As we're getting ready to wind down at the end of the day, we save the best for last, and we are happy to have Blair Fraser with us. He is the Director of Global Operations at UE Systems. He also does this very interesting podcast called Maintenance Disrupted. I'm not sure if you heard about this or not. If not, then you need to check it out. But I am going to hand you over to Blair, and he's going to be telling you about bearing lubrication reimagined. So, Blair, it is all yours. I know you
Well,
got this under control. And be
thank
sure
you.
to check out his code and play to win.
That's right. And thank you. I got a little nervous when you said the best for last. I was like, oh, I'm in the wrong
Oh
time
boy.
slot. I should have been in the morning. So for those that are able to join, thank you. I appreciate you joining in here towards the end of the day. And what I'm going to talk to you about is re-looking at the way we call the re-greasing of bearings and how we can leverage more technology to make that process more efficient. And I'm pretty active in the IoT space, and I try to have some conversations with some people in some of those panel discussions. And I fully agree that people are the most important part, and technology can help fuel people make better informed decisions. And what I'm seeing in technology in general is that we're doing a lot of work to identify a failure in a bearing. We're doing it. It's what I call a race to identify the failure. And I believe that if we just spend a little more time on that proactive part of eliminating, I'm sure everyone agrees here because it just makes so much sense to eliminate that failure from happening in the first place. And really, when we look at it, there's lots of studies, and I'm sure there's lots of references here in this community. And it should be no surprise to anyone in this community that, a lot, and whether it's 80%, 60%, depending on the study, the primary cause of premature bearing failure can be traced back to a problem with lubrication, right? And it's not just the over or under lubrication, and it's not just contamination. There's other aspects of that. So when we're looking at reimagining bearing lubrication, is how do we address and try to eliminate the causes that can be traced back to a problem with lubrication. And I was going to give you an example here. Read the sentence below and count the number of F's in the sentence below. I'm going to give you just a few seconds here. So count the number of F's. Right? What's going to happen if you come up with 3, you're wrong. And there's actually 5. And what this shows us typically is some reason in our human brains, we don't count the word of. We don't count the F in the word of. Right? So we got finished, files, okay, there's 2 there. And we skip over of. Why? There's some human reason for it, and I have no idea what it is. But there's always an aspect for human error. And I think that's really where technology can start to come in. Those repetitive value added tasks is what we need to focus technology on. And really focus the humans, the people, on enabling those value added tasks. So some of you might be familiar with ultrasound, and I'll give you a quick overview of what ultrasound is. Essentially, we're measuring high frequency noise, way higher than we can hear with our ears. And essentially what correlates to is the sound produced by friction. So the friction impacting happening in a bearing, right? So then it becomes kind of obvious of why ultrasound might be a really good fit for you in your condition monitoring program to look at the health and lubrication needs of your bearings. So when we look at friction as a whole, it can tell us a lot, right? And we start to focus on things about condition monitoring, condition-based maintenance, whatever you want to call it, predictive maintenance, although it's not typically too predictive at all. But if I use the word condition-based maintenance or condition-based monitoring, what's the condition of the bearing we're trying to monitor? What's that one variable? And friction can tell us a lot if we track it properly. It can tell us poor lubrication, right? What's the purpose of lubrication, of grease in a rolling element bearing is to, there's a lot of other things from corrosion point of view and things like that, but the primary function is reduce the friction. In fact, it's in the name of a rolling element bearing is an anti-friction bearing, right? It can also tell us, if it's impacting and things like that. So when we look at this as a whole, and some of you might be familiar with this, and you might do a lot better justice than I'll do to this, is when we look at what's called the Strybeck curve. And I'll explain this the best to my ability. And for any of you tribologists want to add some comments in here, by all means, feel free to do so. So when we look at friction in, compared to the viscosity times rotation, speed, and load, essentially the operating context of that bearing, the first regime they talk about is boundary. When, you have essentially, there's no film separation, there's metal to metal contact, right? And obviously metal to metal contact is going to give us the highest level of friction, or in our world of ultrasound, the highest level of decibels. We get into the next category, which is the mix. And this is ideally where we want to be. Some load to support by the lubricant film, but still have some contact, right? It's that very thin film. And I've heard so many grease specialists and lubrication specialists tell me the exact number, and I always forget about how many millimeters thick that grease needs to be, given it's the right grease, contaminant free, and all that kind of stuff to actually support that ideal level of grease. And then if we move out of that, we get into the hydrodynamic, which is almost counterintuitive in my world, and I come from the electrical space, was hydrodynamic. When there's actually so much grease in there, we have opposing directions of fluid. And we've all seen that when we've greased a bearing too much. What starts to happen? The friction starts to increase, it starts to heat up and things like that. So knowing where you are on the Strybeck curve can greatly impact the life of that bearing. But typically we don't look at it this way, right? We look at other means of measuring that bearing in terms of velocity, movement, and things like that. So when we look at that film thickness, there is an ideal location. In fact, what I've learned is that you don't want to be at that bottom of that curve, the lowest point of friction, because it doesn't leave much room for error. In fact, where I have that word friction is ideally where you want to be on this Strybeck curve. You want to have, in between. You still want to be in the mixed regime, as they call it, but you don't want to be, because the way up back to the boundary of mechanical, that's where a lot of damage occurs. So knowing where you are in the Strybeck curve can truly reimagine how you look at bearing lubrication. So what we developed was a system that, through our sensors and ultrasound, is going to measure that friction in real time. So consider it, you're building a trend of that Strybeck curve of what's that friction over that bearing in real time. That information is getting sent out. And this is what, looking at reinventing or re-looking at those non-value added tasks. So you're measuring that friction 24/7 through all operating contexts, when it's off, when it's on, variable speed, different temperatures, all that kind of stuff, to get some insights of that friction. And what we can start to do is look at that friction and start to identify certain insights. Those insights are traditionally is, when does a bearing require lubrication based on friction? How much lubrication is required, of course, based on friction. And then if I enter a failure mode beyond friction, how quickly am I starting to fail? And those questions can be answered by trending this friction in real time. So what we allow is the user, fully automatic mode, to go out there and, using friction as its guide, to go out there and know exactly where it is on that Strybeck curve, and very strategically and very slowly add the right grease to that bearing to restore the friction level, right? We have case examples. I'm going to show you what that data looks like when we're in that far left, that boundary of the Strybeck curve of when we have metal contact, and seeing that just a little bit of grease hit that bearing, what happens? And then, of course, if we have over grease, what happens with that as well? So the benefits of remote condition, friction-based lubrication, it's feedback. So we know exactly when lubrication is required, know precisely how much lubrication that is required. And if we do this right and we load the single point lubricators, which traditionally have no feedback to them, we have no status of how much grease is left and all that kind of stuff, we know with confidence we're going to use the correct grease every time. We know grease is hitting the bearing, that the maybe remote grease lines aren't plugged and things like that. And of course, we reduce the risk of contamination because we're not walking up to it on a time-based schedule. And the way we look at it is from a friction point of view or ultrasound point of view is very simplistic, right? I know there's a lot of talk, and I'm a big supporter of artificial intelligence and machine learning, but it's very important to only apply it when it can drive additional insights. And one thing we talk about is the use of ultrasound is its simplicity. It's not simple in how it gets the data, but it's very simple on how you can start to use the data. And what we do is we set up a traditional dashboard like this. And what we do is we set a baseline. And it's very common to use an 8 decibel level over baseline, which is an ISO standard, regardless of the bearing. And I can go into more details, or we can chat separately about how to set that baseline, because each bearing, each application will have somewhat of a different baseline. So if there's an increase of friction, 8 decibels above the baseline of a healthy, well-lubricated bearing, it needs lubrication. If it's 16 decibels above, we're going beyond a lubrication failure mode, which I will show you some examples. When you lubricate, you can mask a failure with grease. We actually see that friction go down, but it's not going to stay down. You think about an inner race defect, an outer race defect, a cage failure. Eventually, that defect is going to find its way through, and you will start to see that friction go up. And I have some use cases of that. And if it's 35 decibels, that machine's walking down the hallway, and you're going to pick it up with other senses and things like that. So I want you to imagine with me, right now we're reading 28.7 decibels on this screenshot I took. Imagine that arrow was straight up reading 40 decibels. You walked up with a grease gun. You're using your cell phone. You're watching that friction. You squeeze a little bit of grease into that bearing. What's going to happen is you're going to start to see with every squeeze of that grease gun, the friction start to grow down, right, in real time. And that's really what we got to think about from reimagining it. So we're not just doing it on time-based, we're doing it on condition feedback. And if we take it a step further, what if you didn't have to squeeze that grease gun? What if it could do it for you? So in a healthy bearing, this is what friction looks like. Now, this is on an air handler unit. This is a variable speed drive in an air handler unit. And it's a 24-hour period. This is a very common trend we see. This is what I love to see. This is a healthy, well-lubricated bearing. And I can tell that pretty quick just by looking at the data. Now, this is a variable speed drive. So the question is, does load, operational context, speed change friction? Yes, it does. And let me describe what it does on a healthy and well-lubricated bearing. So this is another way of visualizing this. So you can see this friction trend. If you were to look at this and you could plot 24 hours, 3 days, 3 years, or however much time you want, this is ideally what you want to see. There is a green line underneath there. That is our baseline. That blue dotted line is the lubrication level. When it needs lubrication, that our blue trend line of friction will actually increase. Over top of that blue line, we lubricate. It comes back down again. Of course, yellow is warning, and red is critical. So let me answer the question. Does friction change based on varying speed conditions? It does. It absolutely does. We've done our own studies. Academia has done studies, and our customers have done studies. It's important to note on a healthy, well-lubricated bearing, the change is very subtle. We may see a slight increase, maybe 2 to 3 decibels. Sometimes it's larger, depending on the operational context, but it's not going to be night and day difference. So let's take a look at this. Okay, so here's an example. You can see the initial friction. The baseline was 14 decibels, the peak to peak, and that's the highest point to the lowest point of the friction trend. And essentially what that tells me is there's a lot of impacting going on. And we see this very commonly with the system because it becomes so easy to maintain your bearings. Is people will grease even when it's not at the point where you absolutely need to grease. They just want to watch that friction go, which is fine. And you can set up to automatically do that as well. So what happened here is, 15 cc's of grease was added. And you can imagine if you were listening to this, which you can with our ultrasound tools as well, our handheld tools, is you're going to hear a lot of static, a lot of impacting, right? And as soon as that grease is added, nice and quiet, right? So it dropped that down by 3 decibels, or peak to peak almost reduced by half, right? This is what looking at friction can do for you, right? And if you know what 15 cc's of grease is, it's not that much. So here's an example where, we got into that boundary where we got into, mechanical to mechanical contact, right? And what the system was able to do is says, this system, this bearing needs lubrication. It went out there and it lubricated it. You can see here, exactly, it was 9 cc's, right? We're talking such a small amount of grease was used to restore this friction. And what we found, and I'll tell you, is it was interesting to me, is what we found to maintain that ideal spot on that Strybeck curve is or the system will grease more frequently, a lot frequently than the time-based calculations. But use a lot less grease, and cumulatively over that year, over that life of the bearing, you use a lot less grease, even though you're greasing more often. Again, 9 cc's is just a thimble full of grease. It's typically a rounding error in a grease gun. And what it says here, so it was 4 days ago at the time I took the screenshot, assisted mode, so it did all the work for them, but it recorded the baseline friction was 11, starting friction was 22, ending friction was 12.6. So it got it right close to baseline automatically. And that's what we're talking about, reinventing or reimagining how we lubricate our bearings. Now, this wasn't the smart loop. This was just going out there with the grease gun, but you can see the impact of just a small shot of grease. And this is what we call the aha moment. You're trending that friction and go, just how much grease? I'm like, just put it one squeeze in and see what happens to that friction. And we start to see examples like this, right? So we move from that boundary to that mixed domain or regime. Now, this is an example of, the friction level wasn't high, but as you can see by the squiggly friction line, it was impacting. It's in my opinion, it's not going to cause a lot of secondary damage to the bearing. We would start to see that as it picked up in friction. But what the customer wanted to do at this case was go in there and just put a little bit of grease in. Again, a small amount of grease. And what happened is, you can picture it, the impacting, a lot of noise. As soon as that grease hit, just nice and quiet, right? And that friction actually dropped below baseline, which is absolutely perfect, right? So trending that friction becomes very obvious when a bearing needs lubrication. So here's another example. And I'm always, the first time that we do this, and we can do this remotely, I've lubricated bearings all over the world now through these systems because we can do it through our phone. If a customer gives us access to it, we can do it with them. And I always like to do the first couple with them. And I always call it that aha moment because they're watching that friction. They're watching this. The system tells you, okay, I'm putting in this much grease, and it waits. It waits because if the grease typically comes on the top of a bearing, it has to get pushed all around, turned all around to get all through. A little bit different if you need to purge out old, and I can go into that offline about how you would purge old grease from a bearing first. But we call this the aha moment. The rate at which that friction starts to drop once grease gets in, it may not be at the first half a cc or a third of a cc, but once it starts to reach and push its way around, that drops. Right? And this is a great story because I have kids, and I love this. I don't encourage anyone to go back and do this while you're with your kids. Invest in family time. But what one of our customers told us is, they got the alert that this bearing requires lubrication, and he wanted to get, have it set up so that he would go and give it permission to lubricate, and it wouldn't do it on its own, and that's their choice. Essentially, he said, yeah, okay, give it permission to go ahead and lubricate. It went through its step. It may take 30 to 40 minutes to go lubricate that bearing. Right, a simple, small roll melt bearing, it may take 30 or 40 minutes because it's going to do it very slowly and very systematically. Now, when we look at trending friction in a bad bearing, and I've shown you those nice marketing pictures of nice smooth lines and grease hitting it and it dropping, the reality is not all bearings are like that. And I'm sure many of you have, if you're an asset owner, you have some bearings in question, right? So even not knowing ultrasounds, just the information I gave you, look at this trend line compared to those other trend lines, right? You would not want this type of noise, this type of friction and impacting in your bearing, right? This is, on the extreme of metal to metal contact, right? And then I mentioned about, tracking that friction with the VFD in a healthy, well-lubricated bearing. And I showed you that with the air handler unit, it doesn't fluctuate very much. We do see some peaks and valleys. Look at the size of this one, the waves, and if you were to track the speed, it matches to that friction trend. This is an unhealthy bearing. Again, you don't need to be an expert to look at this, right? You should not see a trend like this in that bearing. So here's an example, and again, not to share just the ideal use cases, but it is possible. We see that increase in friction. In this case, we got above the warning, and it was lubricated remotely. The friction was dropped. The system tried to get it down to baseline. What the system will do is actually keep on putting lubricant in or grease in, but there's two stop points. One is it will never exceed the max bearing capacity, and it calculates it. You put that in as a variable, so it won't keep on trying to put it in until it explodes the seals or it overfills it. And the more important one is it's always watching that friction. So if we start to see we're going in that Strybeck curve and I'm still adding grease and I'm moving too far to the right where I start to see too much lubrication, it'll actually stop automatically and say, listen, I got it as low as I could. It's going to word it a little bit differently than this. I got the friction as low as I could, but my friction started going up, which is an indication of overgreasing, right? And this is the case. In this case, there was a known defect in this bearing that lubrication could not overcome. So it didn't want to make sure that it over lubricated it. Now here's another one. This looks like a successful lubrication, right? 4.5 cc's, very little used. You can see there's 88% grease remaining in the single point lubricator, and this can be anywhere in the world, right? It looks like it restored that friction to drop like a stone, but did it, right? And this is the example I get, is you can mask a bearing failure measuring friction with grease, but only temporarily. It will come back, right? So you can see here, I think, so that was at 11 o'clock. By 2 o'clock, so 3 hours later, 2 to 3 hours later, that friction was right back up again, right? So while greasing, and you can use it as a mitigation strategy to nurse yourself through failure. In fact, you can see here we have manual where you can hit that button, it will grease regardless of all stop points if you want to. And we've seen customers use that to nurse their way through failure to get to that planned shutdown. But not everything is perfect, right? Not everything you're gonna have the scenario where the friction drops. And what I want to do is, as we're closing up here, I want to leave you with this example. 2 identical motors on the exact same system running in parallel. They start and stop. This is the friction trend on the drive end, the non-drive end. Perfectly gets up to baseline. The next one, look at the friction trend when starting up. Okay, so it starts up, that friction goes high, eventually within a couple hours, finds its happy spot. And what we found through investigation, the equipment had to be off for longer than 2 hours in order for this situation to happen, right? And me looking at it said it's starting up, it's doing something, and it's finding its happy spot in friction. And the customer said, exactly, that's what I wanted to see. I'm like, you knew there was a problem? He says, absolutely. And they were able to confirm it with vibration, right? Which is a great technology to confirm a very root cause or what that defect is, right? And what they found was an imbalance. So essentially, through the imbalance, it had to heat up to find its quote unquote happy place. Someone might be able to describe this better, and then start the friction was reduced once everything heated up, right? I'm up in Canada. Things get pretty cold here in the winter, and things don't like to sit cold, right? So it took a while for it to heat up, right? But just looking at that from a friction level became very obvious, right? We shouldn't see those spikes when things start up. But what I'll do here is I'll invite you for any questions. This is my email address. Reach out for any thoughts, ideas you have. You can go to our website, uesystems.com SmartLube. Or what I invite you to do as well is we have a sponsor page here and we have a chat. If you have some ideas, want to get more information, come into our sponsor page. I'll be in there chatting back and forward with you. And we can answer any questions or any more information you would need about how to use real-time friction and remote lubrication to reimagine your bearing lubrication program.
Yes, definitely get in contact with Blair, because Blair's the expert here. He definitely knows a thing or two about friction, and I always love that Blair brings it back to the basics. We start off with the Strybeck curve, I love that part, we have to get there. It's always good to, just reiterate that part, because a lot of people, they see it initially and then they're like, okay, this is just a good to know. And then they forget that you can apply it to anything else. Like,
that's right.
That's
exactly.
The fundamentals. We always forget that. Yeah, always forget it. And I think one of the things that I loved about the presentation is that you talked about grease masking failure. So I never thought about it before until you brought it up. And I'm like, oh my God, wow. I didn't, can you tell us a little bit more about that? Because that was like blown my mind.
No, exactly. And then hopefully I'm using the right terms there is, can you grease your way through failure is kind of the answer, right? And right. And what makes it it typically is an exponential, and anyone who wants to see it can show you. We have had, in the controlled setting, we've had bearings run to failure tracking friction, right? So just let it smoke its way out. And it's an exponential curve in terms of friction, right? And how quickly that's growing. And everyone wants to get to remaining useful life. And I think this is a way to get there, of looking at that friction and how quickly that friction is growing. But yeah, what we've seen is you can have that friction, put new grease in, and restore some of that friction level temporarily. Right. And that's the first sign when we do it. When we're starting that baseline, we typically recommend, can you put a very, very small quantity of grease into that bearing? And the reason I asked is going to do three things. One of three things. The first one is that friction will drop, which is an indication that bearing needed grease to start. It'll actually, friction will increase, which means it was over lubricated, or it'll stay the same, which it was running in a pretty happy spot. Now, it's subjective because it depends how much grease you put in and things like that. And we'll recommend it based on the type of bearing and things like that. But we'll put some grease into it. And if that drops, I'll say, just leave it. Let's see what happens, right? And if we come back in an hour and you're watching that, and typically they're watching on their phones, you start to see that friction come back, like, chances are you might have a problem with that. Or it's still a little more hungry and needs a little more grease, right? So we can use that insight. But the reality is, if it does have, and I don't care if it's inner race, outer race, cage failure, it's going to manifest its way in friction. You can temporarily mask that. It's kind of like if you have a fever, you can go up a cold shower and temporarily drop it, but it's going to come back. Right? Advil might take it away for a little bit, but that fever is underlying, and you're going to regret it in a bit, right?
Yes, unless you find that root cause.
Definitely.
That's right. But it's a great. I think it's a very efficient tool to be able to detect what's going on with your bearings. And I love the fact that the guy said, he was able to log in on his phone, put in his stuff, and still be there for his family and being able to balance. Because a lot of operators have that issue. They have an issue in the plant and they have to leave in the middle of the night to get to the plant, change things around, and then come back. So I love that aspect of it. So we do have a question from Henry, and he is asking, do you monitor greases or also hydrostatic bearings with oil? That's interesting.
It
How
is.
can you tie that in?
So can you? Yes. The answer is should you. Or the question is, should you? And I'll speak a little bit to it, and we can take this offline, Henry. And thank you for the feedback on the presentation. Is when we get into oil, and specifically, I'll say sleeve or driller bearings, where it rotates in an oil film, and there's no rolling elements. Is since we're measuring friction, is typically by the time that there's friction produced, you're too late in that PDAF curve, you're too far down the failure. And that's traditionally why you'll see prox probes and things like that used to measure the distance and if it's moving, right? So there's a fundamental difference. Have we seen people do it successfully in monitoring those subtle changes in friction? Absolutely. Can it be used? Can you fill, our lubricators? Do we have oil versions? Absolutely. But it's not like I call, motors, pumps, fans, cooling towers, those things like that. Anti-friction bearings are home runs. Like it's easy. It's a cookie cutter. These ones you need more design input and thinking, and sometimes testing. Like we're doing linear bearings. If everyone's ever seen those, things go back and forth. So it's all about data timing and stuff like that. So the answer is, unfortunately, Henry, it depends. Depends on that application.
No, and that's a good question. And honestly, I think the way that things are moving right now, it may be something that we will see in the future. We're having a lot of developments with technology, being able to integrate everything. So, Henry, you are very future and very forward thinking. We love that.
That's right. And it was interesting. It's people like Henry that came out, and we have an exciting announcement coming out. I might have a little teaser here, but because ultrasound, it's used on all sorts of bearings, but typically it's predominantly, we see a lot of applications in slow moving bearings, which produces very, very little noise to begin with, like less than 1 RPM, right? And you go to these things like, is it even moving? Like, yeah, it's moving. We needed a sensor. In not all things are created equal, right? Just because it can measure that frequency doesn't mean it has the sensitivity to actually pick something up, right? So we're developing and releasing a sensor here shortly, designed for very, very low level friction measurement, if you will, right?
And I think Skylar is definitely one to talk about that. He's asking how large of bearings does the system support? And I know Skylar has some very slow moving rotating equipment on his side.
So in terms of large, excuse the pun, but size doesn't matter. Reality is what we're concerned about is the level of energy that's produced from that bearing, right? And and it's interesting because people, well, can it measure the speed? And if you were to have a bearing on a ceiling fan, a traditional ceiling fan that they're quiet, they have no load, even though it's spinning pretty fast, there's not a lot of energy being produced until it starts to fail or wobble, right? So really what matters is the context of that piece of equipment as well, is not just the size of the bearing and the speed, but also the operational context of it, like what type of load it's on and things like that. So we haven't come across on the large size of a bearing that we haven't been able to tackle. What we do have is traditionally on the very, very, very low end, small little bearings that have no load. Think conveyors. Think conveyors that they're not driving something, they're spinning in the air. They're not producing a lot of energy. Okay, and so I see his question pop up. Yeah. Love it, Skylar. So we have there's two answers to that. What's the system capacity? So from a grease perspective, is we have these. This if you can see me, this is a 250 milliliter. I should have a grease pouch somewhere behind me. But for this full of grease, 250 is by far the most common. Now we have ones that's double the size, 500, and we have one that's down to 60. But that's just the capacity of this grease, right? You don't, obviously, you guys being grease specialists, you don't want grease sitting in here for 10 years. It's going to separate. It's not going to have its properties, right? So you want to make sure you turn through it. But in terms of how much grease will it output through the end, I'll say the system decides, but you give it a framework. So you can program it to say, every time you dispense, I want you to put as small as 0.3 cc's, which you're like, well, right? It's your thumbnail, right? To over 2 cc's, right? And if I was to do this, you would see a long string of grease come out, right? So the system is adaptable to how much grease you want to put in at a time, right? What there is built in is a time between. So if you have a very large bearing and you're going to grease it at 0.3 cc's, and you're going to try to wait, a minute or two in between to make sure that grease gets pushed around, that friction to drop, and you have a large bearing that requires 50 cc's, well, you're going to be till Tuesday trying to grease that, right? So consideration on the size, the cavity size of the bearings goes into what we'd recommend for the setting, and you can change it at any time as well.
All right, that's Skylar, great questions. And I'd really, Skylar, Henry, everybody else who's on this session right now, connect with Blair and definitely chat with him at the UE Systems booth. If you don't know, he also has a podcast called Maintenance Disrupted that he talks a lot about other maintenance stuff as well. So check that out. And thank you all so much for your time today. I know we have another panel starting shortly, so thank you so much. And thanks,
Thank you, everybody.
Always great. Bye.